The level surface drops down from the horizontal plane at a rate of 8 inches times the distance in miles squared.
I'm not kidding. And bam, there's the radius of the Earth. 3 coplanar points. But look what I did here. 3 coplanar points. 3 coplanar points.
But why would you want that level?
When we say flat, as just a common parlance way of not saying lots and lots of words, when we say Earth is flat or flat earther, we do mean that you think horizontal is level.
I'm saying, personally, I believe the things that you teach your child, your autistic child, is psychological child abuse.
Like that water is level?
No, you teach your child that level is a horizontal plane, which is not true.
Yes,
and the implication of that is that you are teaching your child the Earth is flat.
No.
Yes.
Today we have Jesse Kozlowski. Wherever you are when you're talking to flat earthers, bring them to Walter's blog. Show them how, take screenshots, post it on social media. Show them how we have literally measured.
3 coplanar points.
I have literally photographed, and Walter has literally modeled the curvature of the Earth. They all agree, and that's how we know the Earth is a globe. And that's all there's to it. And that's how we know it can't be flat. So please share this information.
And you and I have had this conversation before. We both became aware of flat Earth, jumped in, pretty naively initially.
Right.
I've gone round and round with it, and at this point, I'm thankful for flat Earth because I'm blessed to have a profession that I really enjoy. I've loved surveying since getting out of high school, so I've been doing this a long time, and really thought I knew something about it. Well, the research that I've been doing over the past couple of years, I've learned a lot that I just didn't know about, and it's just great. I'm really enjoying it. And if you go on my channel, you'll see I did not set out to debunk flat Earth. I was more about, hey, can I do some measurements that will show me what the shape of the Earth is over this short distance, say a mile, or across some water? Hey, let me try it across a lake. I'll use the lake as a level. Exactly. I've done several of these tests, and you can't fake that. I mean, the observations will reveal the truth of the matter, and especially when you repeat them over and over. And I do that. When I've gone out on a weekend to do that, I'll spend the day there, and you're observing in the morning from one side, you go over to the other side, again you observe, and then you do it again in the afternoon. These repeated observations agree with each other, to very high reliability. So I've done long tests and short tests. I've gone down and met with Larry Scott and really owe Larry some time. We really need to do a hangout and show the work we did over the couple of days I was down there on some pretty long lines, 6 miles, 9 miles, 11 miles. And we're planning to do like a 24-mile line. And I mean, really what we're enjoying doing is bringing back old school survey, doing old triangulation, doing solar azimuth observations, which I used to do them all the time in the 80s, but I don't really do it anymore, but I'm going to be doing it. Larry's got a really good method down. He can crank out a solar observation in 5 minutes. Boom. And he's like, and he's a pencil and paper guy, just gets it all down there. It's awesome. So, that's what I'm saying is it's not about debunking flat Earth anymore as much as
it's not. It's really not.
Going back, reading about the history, about how we can't come to know the size and shape of the Earth, looking at what they did, and enjoying kind of I guess some people like to do reenactments of the Civil War, or they like to do anachronistic medieval stuff. I'm enjoying bringing back some of these older methods and exploring them and trying them and seeing if I can do them. So it's fun. I'm having a good time with it. It's good.
Yes. Today we have Jesse Kozlowski.
Before we get into that, I'll just make mention of what kind of motivates me to stay involved with this whole flat Earth thing. I guess found out about flat Earth in 2015. And then once I was in, looking at some of this, I made a video called Geodetic Surveyor Straightens Out the Flat Earth, naively thinking, well, that, they just obviously hadn't heard of geodesy, and that'll take care of flat Earth. So instantly after that, videos were coming out about geodesy, and geodetic surveying proves the flat Earth. And over here on the left, we see different surveyors claiming that they never compute curvature in their work. And, you know, that's good enough for a flat earther to just say, well, that means the Earth is flat. Well, it really just means that that surveyor does not compute curvature in his work. And there's a lot of surveyors who don't. I mean, they just do what's called plane surveying because they just do a short extent of a survey. Or if they are working on long projects, highway projects and other projects, and they're not doing the calculations, that just means someone else is. So I do what I can to try to help people see this and try to understand the differences here. So I'm just waiting for the next flat Earth survey or flat Earth video to come out, and you know, it'll be the globe proves flat Earth. So whatever we bring forward, that ends up being you know, proof of flat Earth.
That is how they do it these days. Yes, yes.
So
they're busy spending their days explaining why their flat plane looks exactly like a globe every time we measure it and photograph it.
But it couldn't be curved. No.
Mm-mm.
So
when we say flat, as just a common parlance way of not saying lots and lots of words, when we say Earth is flat or flat earther, we do mean that you think horizontal is level. So here's the deal. You tell me what you expect to see if the Earth is flat, and then we'll tell you what we expect to see if the Earth is a sphere.
Isn't
so, go ahead.
Flat, McToon.
So
there is topography. Surveying, right, means that the Earth isn't flat. You measure topography. Ask your guy that's pretending to be a surveyor, right? That's not flat, is it?
Hold on. Let's be clear, Bev. Are you going to just say clearly right now that the main surveyor is lying about being a surveyor?
I'm going to say that the surveyors would measure topography. Now that is a change.
Well, are you going to say
elevation,
or stop saying that the main surveyor?
I don't know. He'd have to prove that he's a surveyor, wouldn't he? He would, in order for that, I would need to know he is a surveyor.
Excuse me.
Okay.
Main surveyor, are you a licensed geodetic surveyor in the state of Maine?
I am a licensed professional surveyor in the state of Maine.
Very good. Okay.
Are you bound by any ethical code or anything of surveyors?
Oh, you like to ask that question, don't you?
That's the first time I've ever asked it, to be honest.
Actually, Bev, you've asked it to me on Twitter.
Oh, yeah, you never answered, did you?
I actually did answer, Bev.
I can't remember. Just remind us.
We have a standards of practice which we must follow.
Yep. Code of ethics, to be honest, to the public and represent your trade.
In Maine statute, it is called a standards of practice.
Okay. And you would be bound by that, right?
When performing my professional duties.
Okay. And are you performing your professional duties at the moment?
I am representing the profession of surveying at the moment as an individual.
Okay. Fantastic. So, when we do our test and we establish, first of all, step one would be to establish a horizontal line. Now, can surveyors do that? Over a mile.
So listen, we could establish a horizontal line.
Yep.
The ground will tend to drop away underneath that horizontal line eventually, assuming that the topography is consistent.
Okay, so
like
like say along your along your canal, your canal. If we were to establish a horizontal line at one end and make that horizontal line stay horizontal to that point where it began, then the ground will drop away underneath it eventually.
Okay, so we establish that horizontal and we make it go past the half-mile mark and all the way to a mile mark. So we have one horizontal line across 3 posts. Can a surveyor do that?
If that's what you want the surveyor to establish, the surveyor could establish that but it's not the same as transferring an elevation.
Brilliant. But that can be done, right? So that can be done. So we can have 3 posts, one at a mile, one at a half mile, and one at the other end, right? All with marks on them that will be on the same horizontal.
But different elevation.
Well, just the same horizontal, right? That's all we're interested in.
But the elevation would have to be different.
Yeah, I don't know whether they'd be bothered about keeping telling me that we were a different elevation or anything. So it can be done. They can put 3 marks on them posts, right?
They'll all be a different elevation.
Well, they would be on a horizontal, though. That's all we're bothered about, right?
The surface of the Earth is curved. Therefore, 50 feet at the beginning
horizontal, though, can't you?
Will not be 50 feet at the end of the mile.
You can have a horizontal, though. That it is possible for surveyors to establish a horizontal over a mile.
Why would you want the surveyor to do that?
Because that's part of the test.
What are you testing in your test?
We're just the level and horizontal, right? Is there a connection between the two?
You're testing definitions. That's not how we test definitions.
No, this is a practical test, right?
You start with the right definition first.
This is a practical test. In reality, we've just established that surveyors, like your profession, supposedly, right? Your friends can establish a horizontal over a 1 mile distance.
Bev, do you think that 50 feet in elevation at the start of the mile is going to be 50 feet and horizontal at the end of the mile?
Do I think that?
I'm asking you that.
Yeah, I probably do, yeah. Let's say yes. I imagine that if there is no change in elevation, that means it is a horizontal. Yes, that's what I imagine. Or, in fact, I know it.
So
you know it.
Yeah. The test. Can we go back to the test, or are you scared of it yet?
So, datum, any level surface to which elevations are referred, for example, means sea level. You're going to love this part. Listen up carefully. Also called a datum plane, though not actually a plane.
Okay. Fantastic.
And it has this nice graphic that goes with it that shows mean sea level as an example of a datum, and it shows it as an arc. You explain to me how an arc is horizontal, because you seem to think that mean sea level is horizontal. But here is a surveying textbook, Bev, that explains the principle on which surveyors actually operate every day. Explain how it's a curve, explaining curvature corrections that must be used. And you are saying it means horizontal. You are wrong, Bev. That's not how surveying works.
Is it licensed geodesic surveyor? Yeah, no, he's never actually said that.
No, he's not a geodesic. He's a geodetic.
Okay, sweet. Yeah. What's the difference?
Surveyor. Geodetic is a word. Geodesic is not what.
Yeah, okay. What's the difference between that and a normal surveyor?
That is it. My goodness, my focus keeps going out. That is a normal surveyor. A geodetic surveyor is a normal surveyor. Okay. There is a subset of geodetic surveying that they call planar surveying, which they can't do, the geodetic parts of it because they're not not qualified and trained.
Difference? What's the difference, please?
Difference?
Yeah.
The difference between a planar surveyor and a geodetic surveyor.
Yeah, to you.
So a planar surveyor can only work in a certain within a certain range because it is if you get into a larger area, you have to take into account the curvature of the Earth.
What's that? What's that area?
I don't know offhand, but when
I heard it was 100 square miles that planar surveyors do, and then anything over that is your other type of surveyors, right?
Yeah, it requires geodetic surveyors if you're over that amount.
Over 100.
But
it depends. To 100 square miles, that would be planar surveying, right?
Yeah, so it also depends on the margin of error necessary, right? So I suppose if they need a tighter margin of error, then you would not be able to do planar surveying up to 100 square miles. It'd be smaller depending on the needs.
Or you could just do geodetic surveying all the time and save yourself that trouble.
Oh, so there's no need for planar surveyors then?
No, you don't have
is that
to,
what you just said?
No. You could save yourself the trouble of having to convert back and forth, worry about, oh, do I do plane surveying here or do I do geodetic surveying here? Just do geodetic principles all the time and save yourself the problem.
So there is definitely a difference between these surveyors then, right?
Yes.
Okay. So what sort of tools would you say a geodetic surveyor plays or uses instead of a normal, just the average surveyor?
I already said, Bev, a normal surveyor is a geodetic surveyor.
Okay. So an auto level then, what sort of tool would that be?
It's an auto level.
Which type of surveyor would use an auto level?
Any surveyor can use an auto level.
Okay, because it establishes a horizontal plane of reference, right?
It establishes a horizontal plane that you would make measurements from, and then you make curvature corrections as you need to.
Curvature corrections within the horizontal plane?
Curvature corrections to your measurements after the fact.
You make curvature corrections to your measurements?
Yes.
Oh. You not just sort of measure what you measure when you look through the scope?
You measure what you measure, you write that down, and then you apply corrections as necessary.
Okay, so when is it necessary for you to apply corrections? Because I've never heard of that.
Well, you can look at the National Geodetic Surveyor. You can look at the National Geodetic Survey manual on geodetic leveling. It will tell you.
Okay, can you not tell us?
I'm sorry?
Can you not tell us?
What is it you want me to tell you?
When the corrections have to be applied?
So, all right. So I think the question Bev was asking was when or how do you apply curvature corrections when you're in the process of doing surveying work?
When you cover a certain distance, you need to start applying curvature corrections to meet certain accuracy requirements for whatever the project might be.
So can you give an example of what a requirement might be, and then how you'd and what distance might be the right?
Well, actually, plane surveyors do account for curvature anyway in their elevations. So you always need to apply curvature corrections to your elevation. I'm saying that differential leveling techniques done properly will account for curvature automatically when you keep the foresight and the backsight relatively short and equal through the entire level. Well, actually, plane surveyors do account for curvature anyway in their elevations. So you always need to apply curvature corrections to your elevation. I'm saying that differential leveling techniques done properly will account for curvature automatically when you keep the foresight and the backsight relatively short and equal through the entire levels. When you're using your theodolite or your total station and you're measuring those distances, you need to apply the 8 inches times the mile squared elevation correction. It's expressed a bit differently for surveying because you understand 8 inches times the mile square. We're mixing units there. We've got to have everything in the same units. So the correction becomes 0.024 times feet expressed in thousands. So a mile would be 5.28. And that's squared.
Okay, so that would be the curvature for a certain point, right? Of a imagined radius, right?
It's not imagined.
The test would have a horizontal. We'd have 3 points on 3 posts that are marked as horizontal. Then what we do is the next part, right, is really easy. You just get some hose pipe, right? And you lay it down by the side of these posts. Yeah, that's easy enough, right?
I'm listening.
And we put vials on the end of them. So we effectively turn this water level big long tube that we'll put a T-junction in the middle of it as well. So we can put it up against each of these posts with the vial, strap them around it, and then we can fill that water level up, can't we?
So are you establishing a horizontal line across that distance, horizontal to the beginning, or are you establishing an elevation, the same elevation?
The surveyors did the horizontal at the beginning, right? They made 3 marks that were horizontal on 3 posts. They did that.
Who's they?
The surveyors that established the horizontal. That's what we just decided before, right? You remember?
Okay, so you're gonna hire some surveyors to come do this?
Yeah, why not? Like
Okay,
professionals.
So you're going to put in 3 posts, and you're going to say, okay, start at this post, and I want you to use a horizontal plane and mark with the horizontal plane that's perpendicular to the plumb line, right?
Yep.
Or orthogonal is the better word. Yep. So from post
establish
1,
that horizontal all
2,
the way across
to post 3, right?
No, a horizontal. I'm saying horizontal, the same horizontal.
Right? So now, are you saying horizontal, or are you saying you want the same elevation at each thing to the
that's
Do you want me to just say it again? I will confirm. We want a horizontal, right? That is
so you're accounting for curvature then.
Straight line.
A flat plane. Okay, so when you do that, if you say those words to the surveyors and don't try to confuse them by telling them you want elevation.
I'm not going to confuse anybody.
Then,
do you think
then you're going to have
confused?
By you, absolutely, because you're, So what's going to happen then is you put your mark right here, right? You got the pen. You put your mark on the first one. Here's what the surveyors are going to do. You go to the next one. It's going to be higher.
What, the horizontal?
And you go to the
higher.
Yeah, you go to the final one. It's going to be even higher still.
No, we're just doing a horizontal. What do you mean higher? How can it be higher? Higher than what?
Because the surface higher in relation to the canal that it's next to, right?
Well, it's a question for Jesse. I just want to know, is the level a drop from the horizontal? A measurable drop from horizontal?
Let them dance.
There you go.
Yeah. Jesse, did you hear that question from Bev? Make sure you're unmuted, Jesse. When you join, is muted. Ask again. Try thinking here. Jesse should be listening.
Go ahead. Sorry, I was on mute and I just came back in.
Right, Jesse. You said the level is not horizontal. So, is the level a measurable drop from the horizontal?
I did not say that the level is not horizontal. I said horizontal and level are coincident with each other at one point only, and that's at the plumb line where the observer is.
Oh, yeah, I heard
that. The level surface drops down from the horizontal plane at a rate of 8 inches times the distance in miles squared. How many times?
Measurable, right?
My question is, how many times? Oh, yeah, it's measurable. It was derived.
That's all I wanted to confirm.
You can measure this. Have you tried measuring this?
Yeah, so you are saying that a water level drops away from the actual level. You know, when you set up an auto level.
No, I didn't say that.
They're different, aren't they?
No, not really. An auto level.
George, I was asking Jesse, what are you doing?
An auto level.
Are you speaking for Jesse, George?
I can't join in. You can't either, man.
George, let me talk to this man.
Go ahead, Jesse.
Thanks. Okay, so how many more times must I explain this to you? I've explained this to you on Twitter, on YouTube, and now we're here in person finally talking to each other.
Yeah.
How many more times?
You're saying that level drops from the horizontal. A level is a tool that establishes a horizontal.
My question to you is, this is my question. How many more times do you want me to repeat this same answer?
One straight answer. Give him a straight answer.
All right, Brian, I'm gonna have to lose you from the call. Only Try Thinking and Jesse Kozlowski are the only two persons should be heard right now.
So that's my question to you, is how many more times do you want me to repeat the identical answer I've been giving you? I don't know. Is this months now since you started following me on Twitter? And
okay, well,
can I go
over it then and tell you what I understand, and you can just confirm or deny it, right? Just to make sure. You're saying that you can set up a level.
No, I just asked you a question. I'm asking you this. How many more times are you going to ask
just this
me?
one? Just this one, Jesse.
So
if you make it sure and let everybody know that you have definitely answered the question that I've asked, then that'll be the last time, Jesse. Promise.
So this is it. Drum roll. This is it, right, Brian? What's your name, Bev?
Do you know the question? Do you want me to repeat the question again?
Yes, you're going to, but I wanted you to answer me that one question. How many more times? You're saying this is it.
Right, yeah. If you answer the question this time properly and not obfuscate it.
Have you seen my answers before?
You've never really answered the question. That's why I keep having to ask to clarify, Jesse.
All right, let's try it.
Okay. Do you want me to give you the question then from full?
Yeah, let's pretend it's the first time.
Okay. I'm at the side of a canal and I have set up an auto level. Right, that is establishing a horizontal line of view, right, through the crosshairs.
Correct.
Right, and now I am at the side of a canal. Now that canal is water level. It is horizontal too, I say, but you say it drops away. Now, can you measure that drop of the water level away from the horizontal level of your auto level?
Perfect. Let's try to, Jesse, address you without interruptions. Go ahead, Jesse.
Yes.
That's pretty clear.
Can you do it without using perspective?
Why not? Why not?
Whoa. I don't think that was that it. Was that it? I heard Brian. I heard George, but it was supposed to be Jesse and Bev, like sorting this out and sealing it up for the last time. So let's give him an extra minute.
So you say it can be measured. What sort of distance can it be measured at, please?
What distance would you like to try to measure it at?
I don't know. I'm asking you, what distance can you measure it at? All of these people around here are thinking you can do it. So tell these people at what distance you can measure the drop of the water level from the auto level, please.
And we're looking in that direction, which looks that way. See how that looks? You're looking out. Okay. And so the curve drops away from the horizontal tangent downward like that. That's how it works.
Right.
Yeah. I don't know why people can't understand that. You know.
Seems pretty straightforward to me, Jesse.
All right. Top, we have A and we have C. The blue shows the water level. All right. Bev is going to have a surveyor set out a horizontal tangent line or a horizontal line going from A to C. That's the black mark. Okay. Yeah. That's our horizontal. Now, Bev is going to take this water level, fill it up so that the top of the water level coincides with the horizontal line at A. And then he expects to go out to C and see that the water level at C, in that water level, the water itself will agree with the horizontal tangent. That's his claim. Our claim is what's going to really happen.
Wow. Whoa, George. Can you just say, don't say our claim.
Bev, be quiet.
All right. Let him speak for everyone then. Go on.
All right. So for those of us that understand that the earth is curved, this is what's actually going to happen. You're going to have your water level go from A to C. You're going to fill it up at A so it agrees with the horizontal tangent or the horizontal line. And then the water will seek its own level so that the height of the water pipe at A, the water at the top of the pipe is going to be at the same height at C above the curvature of the earth, and there will be a gap between the height of the water at C and the horizontal line.
Hey,
and
George,
that amount will be 8 inches in a mile. If you go back to point B, it will be 2 inches to the point where you get to A, that there won't be any gap. So the further you go out from A towards C, the more of a gap there will be between the top of the water on the water level and the
So, George, when it looks like your first drawing, when it looks like that, what are you going to say?
Oh, I'll concede. I'll say the earth is flat. And I'll scream from the rooftops.
The earth won't be flat, though, George. It won't make the earth flat. There will still be mountains and valleys.
Yes. We get it.
It will just make level horizontal, right? Will you admit that?
I'll declare that the earth is not a spherical planet. How's that?
Declare that level is horizontal, right? Because that's what the test is, right? It's a test to show that level is horizontal.
It's simple.
All right, fine. If you want to define it that way, fine. Okay.
Thank you.
Today we have Jesse Kozlowski.
Figured it's about time we show some of the results.
I'm looking forward to this, man.
It's the reason I'm going into this in some detail is because a lot of flat earthers are looking at what we did here at Lake Pontchartrain. So try to understand the importance of this. So there's no hocus pocus to this data, and we'll get into this a little bit more. So in a nutshell, the system that GNSS operates in, or is referenced to, is a three-dimensional Cartesian coordinate system. It's a rectangular coordinate system, and any point P can be described as having coordinates X, Y, and Z. And that's how it works. It isn't latitude and longitude. It's not elevations. It's Cartesian coordinates X, Y, and Z. Now, once you have those coordinates, you can do things with them, such as convert them to latitude and longitude and ellipsoid height. Keep in mind, this is a three-dimensional system. So it's not only latitude and longitude, it's latitude, longitude, and ellipsoid height, height above or below the ellipsoid. But we don't have to do that. You can leave it right here, and you're going to find out that in the test that we're going to look at, these are the coordinates that we ended up using that reveals the shape of the bridge. So back to this. Customarily, what we normally would do with our survey data is not leave it in X, Y, and Z Cartesian, but to go ahead and convert it to latitude and longitude and ellipsoid height. And once we do that, and here's the math for that. This was included in the other video I did. Just converting, you can go from latitude, longitude, and ellipsoid height to XYZ, or XYZ to lat, long, and height. And once you do that, you're able to develop elevations. Okay, so you're going to take the heights that are referenced to the ellipsoid, and you're going to apply a geoid model to arrive at elevations. And that is what we normally would be doing in day-to-day survey work. And it would look like this after you've converted to latitude and longitude. You're going to planarize that, because ideally you want to be working in a very simple system, simple trig, simple geometry, X, Y coordinates. And, nobody really works with latitudes and longitudes when they're doing house stakeouts or construction stakeout or property surveys. We're generally planarizing a small portion of the earth, which could be a whole state or a county or even a little neighborhood. So what you're going to end up with are X, Y coordinates, and we can make use of these types of geometric arrangements, either using an intersecting cone or cylinder to develop these northing, eastings, or Y, X coordinates. And And that's what the United States state plane system is built on, and also the worldwide system used, which is called Universal Transverse Mercator, UTM, and certainly all the countries in the world have their own localized projections for their countries. So here's an example just showing you this data that was collected on the causeway. This is in Louisiana, South Zone, state plane coordinates on the North American datum of 1983, adjustment 2011. And here we have the northing and eastings, and here are the elevations. And you're going to find out that this causeway is very level. They built the thing to be level, except for the marine spans and the humps where boats go underneath of. Otherwise, this thing is level, and you're going to see that. These points are approximately collected about every 10 meters or so, and you can see how level they are. And this is in meters. So we would take these types, normally, what we would normally do in surveying is to take these coordinates and put them on a map. Here's a USGS 7.5 minute topographic quadrangle map. Here's Mandeville. And the coordinates on the side are latitude and longitude, but also UTM and also Louisiana state plane coordinates. They are here too. And what I've done here is just taken that topographic map into my global mapper program and plotted the points collected as northing easting values on this map. So that's your normal use of GPS and surveying, is to create a map for some purpose, whether it's for design, for engineering design, or a property survey or something like that. This is how we would normally proceed. And here's another map of the same area, and this one is in UTM coordinates. So that is the normal way of doing business day to day as a surveyor. What we're going to do here is not planarize these, but leave them as X, Y, Z coordinates. And so we're going to basically be just dealing with the actual vectors themselves rather than projecting it to the ellipsoid or to the ground. We're going to be staying right in this Cartesian system. Also here, this column is indicating the precision at which this data was collected and processed. And
is that 0.02 meters?
Yes, 2 centimeters.
Wow.
Horizontal, 5 centimeters vertical. We're going to say that the vertical is good to about a decimeter, which is what, about 3-4 inches,
so
right?
within 10 centimeters.
What I'm getting at here is this whole idea about perspective does not affect the actual physical location of where these corners are. The dimensions are going to be the actual dimensions no matter what the visual looks like. So keep that in mind as we start to look at some of this data and some of Soundly's pictures, because people are just really struggling with what is obvious. So here's a small test I did on the 6th of January, and that was a Sunday, and this is on Little Tensas Bayou. I went back there, this is a year later, and I measured the reciprocal zenith angles across that. It's about a 6-mile stretch, something like that. On the plane ride home, I did some calculations, and this is kind of rough here, but I'm throwing it in because this is going to be one of these launching points to do another video or a presentation on these results. But I just took the XYZ coordinates of the tops and the bottoms to determine the tilt between them, because obviously the plumb lines are inclined outward, away from each other. And that came out to be 5 minutes, 50 seconds of inclination. And what I measured was 5 minutes, just roughly 5 minutes, 40 seconds. Let's round that off. Those are the adjusted angles.
So you're saying that your measurement over Little Tensas Bayou was correct within 12 seconds.
I wouldn't
of the predicted value.
No, I didn't. I haven't even calculated what the prediction is.
Okay.
And again, I haven't even looked at this thoroughly. I'm just showing you that, hey, I measured zenith angles. That was the tilt I determined there. I'm glad you brought up BLU because I have to give credit where credit's due. This whole tilt thing here that I've been doing this past year, I got the idea from BLU. I'm not kidding. Stanley, you and I were out there in Minnesota at George's, and that's about when that BLU video came out.
Right.
I've computed the tilt between the Washington Monument and the Empire State Building.
GPS does in fact work. Yeah. Regardless of how it works, it does work.
Yeah. So let's all agree it works. We're using it. So that's the point I'm making in this build up to looking at the causeway. So now let's get to the topic here tonight, the Lake Pontchartrain Causeway. I want to make mention that this thing was built back in the 50s, and it was built using old school surveying, transits, levels. Here is the triangulation. This was geodetic triangulation to establish control points out near the bridge, as they were using these as control marks to set out the piles and all of that. And of course, this old school methodology is still used today, except that it's not a manual transit, it's an electronic total station, but the same types of surveying activity takes place to build these large infrastructure projects.
Right, and the triangulations from the other directions all mesh up.
Of course.
They're all self-consistent.
Yes. Yeah. In fact, and when you start to measure these very long lines, and when you form a triangle, you have what's called spherical excess, because these plumb lines are all away from each other, so you're actually going to be measuring a larger triangle. So you have to account for spherical excess. It's an actual measurable, thing.
Right.
It actually exists. And again, they built that thing level across that lake. It's an amazing piece of construction. I don't know how serious to take some of it. So here is a video you can go watch over on Sally's channel. Sally was like at Command Central, up there in the room, doing the live streams, taking the long exposures, the video. And occasionally, us, wherever we were, I know Mike would be out wherever he was, wherever I was, we would kind of call in and get into a live stream. So you can watch this. This was Friday night, I think, doing that first pass on the northbound side.
Yeah, what I call the GPS waypoints.
Yes, that's right.
Where you're recording locations of the surface of the bridge.
That's correct. So here's a little preliminary setup, assuring that we knew what the antenna height was above the road surface. So we put this is a magnetic mount on the car. I just used a survey rod and a plumber's level. This level has a groove in it, so it just sits right on top of that round surface. There's Mike holding it. Here we are measuring. Wanted to make sure everybody saw that it was level. I'm sorry that Bob, the science guy, took so much heat because the thing was his level was like a smidge out. So there's a picture of its level, and we're measuring to the nearest millimeter. If that level was out slightly, how far out would we be? So basically we know what the height of the antenna is above the road surface. I remember as we were doing that live stream, people did not like the sound it made. It was, it makes a beep every time it stores a point. So it's incrementing point by point, and I think I had it set to 10 meters. We had it set to 3 initially. It was way too many. So yeah, distance, 10 meters. There it is, right there. And there's the height of the antenna above the road, 1.53. And there I am going down the road. So about Yeah, I was going about maybe 40, 45 miles an hour. So that's the northbound collection. Now the next day, I did another pass, and you can watch this. This was a live stream that I tapped into, and Soundly put me on, and I was doing that northbound up to the crossover. So this was us preparing that antenna height, and here's Dandy Pandy helping me get that height measured, making sure it's level, and there it is. Looks level, right? Can we all get a check on that level?
Looks pretty good to me, Jesse.
All right. So there I am at milepost 0. That was my 0.85 and headed down the highway. So here's the data brought into Trimble Business Center, the software that I use. Looks like a blue triangle, right? So let's take a look at one of these points. We'll zoom in on point 1294. What you're seeing here, this is a base station called Mary, and we're using carrier phase differencing to post-process these vectors. So that's what this is here. These are continuous streams. And this is the raw data here. So we're zoomed in on point 1294. As I said before, this was on Louisiana, South Zone, state plane coordinates in meters, northing and easting, and the elevation. Here's the latitudes and longitudes. Now, what I'm going to go into next is my attempt at creating a visual, some type of graphic presentation of this data. As I said at the beginning of this presentation, normally you would take these coordinates and elevations and go start making a map. That's how we use the data normally. We're trying to create and show you the shape of this bridge. So what I did is exported the Earth-centered Earth-fixed coordinates, and I converted them into a local system where I was facing eastward, and that's what you're looking at now. So I've just changed the view from looking top down onto the bridge, and now I'm looking sideways eastward. That's what I did. And this, because I don't use three-dimensional graphics programs or animation. I don't have that skill set, but I could do a coordinate transformation that kept the integrity and the relationship of the values intact, but now I'm looking eastward. So let's see what we look at next here. Basically, I'm trying to get this view looking east from inside the Earth. So I've created a plane that encompasses the origin of the ECEF coordinates, which is 0, 0, 0, and forming a triangle that way. And that's the plane that I'm in. It's almost like a section through the Earth there. So here it is. Here I am showing you that view again in my software and what I'm trying to create. And I hope that's coming through. Again, if anybody knows how to do animation and can actually move this camera and make this happen, that would be awesome. But the point being is that what you're going to now start to see is the literal shape of the bridge. So here are, as I showed you before, the Earth-centered Earth-fixed coordinates and their elevations. And now we're going to zoom in on a couple of these points. Here we are at point 44, right here. It's a little masked there, but that's elevation 5.72. There's 573, 570. So the reason I'm doing this for you is that it's hard to visualize where these are in relation to each other. So I've created this view so that we can look at that. You can see that. And afterwards, it starts to dive down again and get back down to the level elevations. So let's hear, this is the large hump. That's 0.1326 at 18.57 meters. See this line right here? That's the chord. I'm going to talk about that in a little bit. That's the chord connecting the from where I started and to where I ended on the level points. I connected two of the level points. So I'll show you that in another couple slides. Now, what are these guys doing? They're checking their pool cues. I found this on the internet, and I'm showing you this is how you check to make sure your pool cue is straight. When you look at that pool cue like this, if it's warped, it's been sitting over in the corner for a long time, no one's used it, it's going to have a bend to it. You're going to see it, right? Makes sense, right? Common sense. So here's what I'm going to do with the view, this cross-section view. I'm going to start to turn it from the side. You can start to see now there's a little hump there and there's a hump there, and turn a little bit more. And each time I turn it, I zoom in so you could kind of see what's going on. This is the shape of the bridge starting to appear as I turn in my software. And that's the large marine span. There's a couple humps one of these humps, Sally, you said you weren't even aware of, right? One of them, I forget which one.
Yeah, it's from the South Shore. If you're looking out at the 8-mile marine span, there's a marine hump directly behind it. I guess it's right about 9 miles.
Right. Oh, okay, that'd be that one.
And it's on the west lane, and it's I'll just from the angle that we normally look at, you don't pick it out, but it is there. You go back and look in the video footage, and you can see the cars.
Now, is it on the northbound side or the southbound?
It's on the north. It's on the southbound lane.
Okay.
Yeah.
That's what this is, the southbound.
Yeah.
Right. Okay. So there's that chord, and in fact, I think my next slide is here's my last turn, and so that's about as far as I could go. And after that, the thing would start to disappear. I don't know why, but the graphics would not allow me to turn this anymore. That's as far as I could get, and so I made a screenshot of that. So here's the side view again, and that's my midpoint, 981. If anybody wants to check this math, that's the chord. It's 28 point, like rounded off to 28.5, let's say, or 28.46 if you want to go to the nearest centimeter. And this is the length from the first level point that I kept in my sample to the last level point. And that's the distance.
So pretty interesting that shape that you just showed us there, Jesse. Would you like to expound on that a little bit?
This shape right here?
Yeah.
Well, it looks curved to me. Is that where you're going with this? I mean, it's kind of obvious, right?
Yeah. Looks a little similar to photography, don't you think?
Yeah. Well, don't let the cat out of the bag yet. Keep in mind, these are level. I mean, if you look at these, except for the humps,
exactly,
these are all at 5.7, 5.7, 5.7.
Right.
5.7. The thing was built to be level above that water. So I don't know. Do we really need to talk about the difference between level and flat?
Exactly. It's level and curved.
Yeah. So
it's actually amazingly level considering the distance that they had to build this thing.
I'm telling you, it's
for 24 miles. They're very consistent, don't you think?
It's awesome. It is
it's an amazing piece
of
architecture, really. Yeah,
it is. The way I phrase it is a monument to the curvature of the Earth.
It is a monument.
It's a man-made monument.
I totally agree with that.
It really is.
That is the globe prediction.
Are you sure? Have you seen all of those different water levels?
I'm sure that is the globe
have
prediction.
You seen?
I will clarify again. I am sure that is the globe prediction.
So, and you can't make this up. I mean, it's just, there it is. I mean, I collected the data, processed it, output it. That's it. you know, here, and all this is just me trying to create views so you can see it. So there it is. Now, let's see, where are we going next? Okay, so there's the chord. You can check that math if you want. This was pretty cool, though. Today I found this morning. I was just doing some searching on I forget what, but I came up. What I was really trying to find was construction, old historic, maybe photography of them building the causeway, and I thought maybe somebody captured some surveyors out there doing the work. I didn't find any of that, but I did find this article. This is from 2011, and somebody, I haven't read the whole thing yet, but he is talking about computing the radius of the Earth using this bridge. So it's interesting. I'm going to take a look at this. I'm just showing you a couple portions of it, but look what I did. I took a sample, just creating that blue circle is the result of doing what's called a three coplanar points in 3D would describe a circle. So I selected one of my beginning points, one in the middle, and one at the end, making sure that I didn't pick one of the humps. I wanted to make sure I was picking, the points here on the level spans.
Right, the lower deck, as I call it.
And bam, there's the radius of the Earth.
Let me pause you here and just
sure.
And just make sure that everybody in the chat or anybody that's listening right now that may have started reading the chat and not really paying attention, pay attention here, okay? Jesse has measured the curvature of the Earth, and he has measured the radius based on that curvature. That's what Jesse did.
I did.
So there is no presupposing R anymore. Okay.
No, we have R.
It has been directly measured by Jesse Kozlowski during Globe Earth Tourism 2019.
Yeah.
So
Roger that.
R is no longer presupposed.
No, it's actually
was.
It's monumented.
Exactly.
It is a concrete monument, 20 some miles long. So here's what happened here. I did a comparison of what, and again, I didn't sit here and calculate this myself. I just picked these 3 points. I guess you could pick a whole sampling of them. And by the way, this is just the southbound lane. I didn't even look at the northbound yet, but we're within 0.5%, right? Somebody can check my math, and again, I didn't sit here and calculate this myself. That is what we see here. So they did a great job.
Measurement, I'd have to say, Jesse.
I think so. That still won't stop me from going up to Maine to do the Alberuni method. I want to definitely meet up with Just a Maniac. He's on YouTube, Just a Maniac. Take a look. A surveyor up in Maine, and he's in my Facebook group, Geodetic Surveying Facebook group, and he did the Alberuni method using zenith angles to the horizon of the ocean from a mountaintop. And this spring, I got to go do that. It's just something I want to do. So what are these guys doing? Well, they're checking the lumber, right? Make sure it's straight. Everybody understands this, but everyone freaks out when they're looking at your photography thinking you have somehow magically changed the shape of the bridge. It just, I don't know. I shake my head. I don't know how to I can't take that seriously, I guess. But that's what they want to do. So here, let's take this circle. We're going to turn it a little bit, turn it a little more. I mean, doesn't that make sense? If you turn the thing and look at it straight on, it's going to change shape. Why? From perspective, right? So that's why I made this video called The Clown Frown Found, because we found the clown frown. And this is the thing that flat earthers want to see. They want to look out on the horizon and they want to see a curve like this. But that doesn't make any sense because the distance from here to here is small compared to the distance from here out to here. And this telescope is set level, and you notice that the horizon does not rise to eye level. This thing's only about 12 feet elevation, yet I'm way over top of that lighthouse. Now, I'm going to just show you this because it helps, I think, get across this whole idea about what is it? The angle of attack? Is that what it is?
Right.
Okay, so everybody should understand that this is a side view, right? This is, you're here and you're looking that way, right? So what happens if we turn that chart? So if I'm holding that chart in my hands and I turn it and turn it a little more, you know, now I'm looking down it and everything's compressed, right?
Yep.
Isn't that what happens?
Right.
So now let's compare that to this. If I set this aside, let me move this over a little bit and bring the chart here. And we're going to just zoom in because this thing's only about, 8 miles away. So we're going to just zoom into this little area right there. Ah, see?
Look at that one. Yeah, you can actually see it kind of going over the horizon maybe right there at the very end.
Yeah, looks curved to me. Dun, dun, dun.
Walter Bislin, shout out to Walter Bislin, who has been in the chat. Thank you, Walter.
Awesome.
For all of your awesome work. Really awesome.
Yeah, I'm just smiling here. So he took the data that I sent him initially and created this app, and it's under development. So let's realize there's still things to be done with it. And I'm not really good at using it. I'm going to try my best to demonstrate it tonight. But so here's a kind of a side view, you know. But now you come over here, and this is about from, like, say, the hotel. And it looks a lot like your photo. In fact, the rental car I had was a submarine car. I had to go underwater. You know, that's over.
So just to clarify, this is your data that Walter has taken, and he has rendered it in a 3D space.
Yes.
And this is what we're getting. Yes.
And
very interesting.
Yeah. It is really. It's just awesome. So, these are he took the XYZ coordinates. He wrote his own program to convert them back to lat and long. He computed, he's done absolute geodetic software writing. I mean, it's like he's got all the calculations in here. It's awesome. So, well, you know, here's the side view. And, you know, you're not going to see the curve from the side.
Right.
You see? That's the whole point. But you can measure it. It's there. You can measure it.
The actual shape. And I'd like to point this out too. We're talking about the actual shape of the Earth. This is like going out and touching it. It's like including a whole other sense. It's not just an observation of a photograph. It's not photographic. It's not optical. There's no refraction involved here. This is us going out and literally touching the surface of the bridge. And saying, this is what the geometry actually is.
So yeah, let's tie it both together. You're right. There's no telescope involved here. This is just 3D points as a result of that GPS survey, which matches the old school survey. Those surveyors who laid this thing out and the guys who built this level across that water. I mean, like I said, it's a standing monument to the curvature of the Earth. There it is.
And this, again, is the Earth-centered, Earth-fixed coordinates. So these are X, Y, and Z coordinates plotted in a 3D space.
Yes.
And this is what you get.
That's right. So, and again, I just want to point out that, you know, that is the northbound. There I am over in Mandeville, turning around, and then I came back and did the southbound. So, and there it is from the side. You're not going to see curvature from the side. Just, you know, you're talking a couple of 100 feet on end to end from the side view. And we're looking in that direction, which looks that way. See how that looks? You're looking out. Okay. And so the curve drops away from the horizontal tangent downward like that. That's how it works.
Right.
Yeah. I don't know why people can't understand that.
Seems pretty straightforward to me, Jesse.
There it is.
Boom! Look at that. Wow. Wow.
Now,
you can even kind of see some refraction going on there.
I think so.
Look at that. Refraction in the observation versus the actual geometry of the bridge, side by side. Compare and contrast. Compare and contrast that with Walter Bisland's models. So we basically have three different things here. We have Walter Bisland modeling it, saying this is what it should look like. You go out and measure it. You say, this is what it feels like. And I go and photograph it, and I say, this is what it looks like. And
correct.
They all agree with each other.
Yes. And keep in mind, he could not import all the points. He sparsely displayed, I collected a lot of points. Let's put it that way. 30,
I thought he said every third point or something like
that. Yeah. Yeah. So he didn't need, in other words, he didn't need, let me get my mouse going here. He didn't need ... That's sufficient.
Right.
To show you the shape. Sufficient, You don't need to fill it in any denser than that.
That is amazing right there, man.
Now I think it is great. And yeah, so he's working on the app. I'm going to just show the app right now without the photo.
Well, hold on before you leave here.
All right.
Let me make this point, and let me make it very clear for every debunker that's out there, every debunker that hears on a day-to-day basis, it's all to do with refraction and atmosphere and optics and all that. All of those arguments are completely defeated. Every single picture that we have showing curvature is now back on the board because here we are. We have measurements showing what the actual geometry of the bridge is, completely independent of any optical observation, and it matches the optical observation. And if anything, the optical observation is showing that there is actually refraction occurring that's making it look less curved.
Mm-hmm.
So all of these arguments coming from flat earthers defeated in one stroke right there, just by that data that Jesse went and collected. So use it. Use the data. Use Walter's application.
Yeah, let's take a look at it. And again, it's under development. So let's just see here. When you go to this his app.
That's awesome, isn't it?
Isn't it fantastic? And that's just what I needed. I wrote him an email. I said, can you work with these 3D points and bring them in? Because again, I have to emphasize, like what I said at the very beginning, this is not something we would normally do as part of a survey, of a bridge. You would survey the bridge and then you'd be producing AutoCAD maps of the structure, to be used in engineering. We do see more and more 3D type use now that we're doing lots of laser scanning, and drones are involved doing laser scanning and photography. And so 3D software is being used a lot. But like I said, I don't have that, and I can barely operate this app. Let me put it that way. But I'd like to learn how. But it's pretty cool. I mean, you throw the points in here, you can see. You come to the side, and this, as you zoom out, and you go all the way to the side, the span flattens out. Just the way it would if you were out here in a boat.
Yep.
You come over here, you go up into the hotel room.
Exactly.
I think he showed me how to.
There's actually a point on the hotel room, right?
Yeah, it is. It's the triangulated
there it
position.
Is right there.
I think I do Control Shift click, and that's the view from the hotel.
Wow, look at that. Does that not look exactly like what we saw during the live stream?
Yeah.
Look at that. That's from the hotel room. So this is all of Jesse's points that he collected from the angle of the triangulated hotel room, because Jesse also triangulated the hotel room while we were there.
Yep. Actually, it's the position of your camera. I nailed that. And like I said, here you can see, you don't see when you go down into Manderville, you're
right.
You're below.
That's all below the horizon. That's right. Yeah.
Yeah. I had to roll the windows up.
You want to flood the car, huh?
I had to put it in amphibious mode. Oh man. No, the next thing we want to do is get those cell towers,
Yeah.
on here.
Absolutely.
Yeah.
Wow.
I think that's all I had.
That's really amazing, man.
So again, this is the initial presentation of what we have. I do, like I said, I'm making an offer to anybody that wants to. If anybody has some ideas on how to render it in some way or do some animations, that would be cool. You can do this with an Android phone. You can log this actual these raw observables.
Right.
Now you have to process that data. You've got to resolve these. These are pseudo ranges to the satellites or cell towers that are 12,000 miles away. I mean, these are actual.
That's a joke, guys. That's a joke.
Yeah. These are actually ranges from transmitters.
Exactly.
They all intersect somewhere.
Which is why it's so silly whenever they start talking about stuff being on the ground. It's so silly. I mean,
I know.
We're talking about it recording distances to objects in three-dimensional space that aren't on the ground.
Right, and that's the thing. I give you the. There's two things. There's the observation file, which is actually recording the data from the satellites, the range data, and then there's the Keplerian orbital parameters to compute the XYZ positions of the satellites.
Mm-hmm.
This navigation file is not your position. This is to compute the position of the satellites at the instant of transmission,
right?
So that you can intersect those ranges to come up with your position.
Right.
That's a lot of wording, a lot of gobbledygook, but that's what's happening.
How GPS works. I mean,
that's how it works.
Yeah. What I'm picturing in my head, Jesse, is people driving like Interstate 10 across Florida,
right.
Which is going to be pretty much the same elevation the whole way. I mean, it's going to vary within reason, but when you're talking about hundreds of miles, if you can take something like that, and pipeline it into into this app where you can actually see that curvature, and you can have everybody doing that. You don't need a camera. You just all we need is a pipeline. People can download this app, go straight from that, boom, put it into Walter's system, and there you go. Directly measuring the curvature.
I wouldn't be surprised if, knowing Walter and the way he just programs stuff, he might be looking at this right now going, oh, I got to get that.
Maybe.
All of a sudden, you'll be plugging in Rhinex files to his app and, boom.
Obviously, if we had that kind of pipeline, that would be, to me, it would just be like, okay, that's the end. What else is there to do? We've actually directly measured the shape of the Earth, the geometry of the Earth. We've directly touched the physical surface with a GPS receiver and know where that spot is. At that point, the geometry, and you're not arguing about optics. You're not arguing about lenses being curved and silly things like that.
It will be interesting to see. Maybe interesting is not the word. What is the word? To see what the next reason is. What is it?
What type of perversion they come up with.
Yeah. I mean, you just got to reach really far for something very obscure and strange. It was strange enough to hear me being told that surveying instruments are flawed and produce, bad results. And, then how did they build this causeway? How'd they build this thing level across there for 20 plus miles? I mean, surveying either works or it doesn't. You can't have it both ways. And so now we've brought it all together. We've got old school survey that built that causeway using theodolites and levels. And now we've done it with a modern approach using GPS and verified the shape of the bridge. I don't know what else there is to say about it right now. And we measured the radius of the Earth.
Exactly. So no more presupposing R. We know what R is.
Yes.
Jessica Kozlowski directly measured it, and anybody else can as well.
Yeah.
And this is the technique for doing it right here. And maybe, Jesse, that'd be worth showing, in detail. This, maybe a little 3-minute video. You take this data. Here's the chord. This is how we measure the radius. You know?
Yeah, I could do that. I could show, the actual. Well, anybody can Google that. Is how do you determine the radius of a circle using 3 points that are on that circle? So, and here we have a huge sample of all these points. We could probably do a linear regression of sampling lots and lots of them to come up with a really good approximation of the radius according to the shape of that bridge. Cutting out the spans, only use the level portions. We would get a very good best fit of where the radius is based upon that structure. So, just
awesome, Jesse.
Just need more time to play with these things, but
yeah,
it's fun. It's fun.
It's amazing the tools and the innovation that has happened by Walter and the methods that we've gone about to just demonstrate beyond a shadow of a doubt the Earth is curved. It's so silly to think that we have to do that, and we don't really. But we do it because it's fun. It really is fun. I mean, it's the photography work that I do is really fun. I enjoy it. I'm getting unique photography that no one else has gotten before. Of course, now we have a few people have done it, and Jesse is pursuing his hobby with geodetic surveying.
Yeah,
and so we are having a lot of fun doing it. But at the same time, I think this type of information is something that it's so obvious and so ironclad now, and we've avoided the final hurdle that they like to throw about with the optics. That I really hope that everyone in the stream first will like and subscribe to my channel, and second,
me too.
And Jesse's channel, and go to Walter's blog. And
Absolutely.
Walter has a channel as well too, though he doesn't do very much as far as the flat Earth stuff on there.